Okay, we're looking at the 25-minute question, and all the questions are kind of already up here, so we're kind of good to go. And let's see what we can do here. We're trying to find two derivatives, the derivative of 65 and then the second derivative, 65. These are derivatives of w. But the problem tells us that w is equal to y. So anywhere we see a y, dy dt, and y, all of these are w's, and that's going to work for us. So we're just going to go ahead and say that the derivative of w is dy dt. Here it is. And we're given the equation. Right here, we're given the equation. So we're just going to substitute in the value of w when t is equal to 65. When t is equal to 65, w is 60. So that's just going to get substituted in 1/15th of 60, 1 minus 60 over 100, and that gets us 8/5. The units here would be workers per minute, though I don't think that they asked us for that. So let's move on. And the next question they're asking us for here is the second derivative. There we go. So we're looking for the second derivative here. There we go. We are going to have to edit all of this out, aren't we? Okay. Now, we are looking for the second derivative. So here we are, second derivative of t. It's the derivative of the first derivative. Well, the first derivative was given to us, and I multiplied through by the 1/15th y, which is what this was. So I turned it into a regular polynomial, and that just made the derivative a little bit easier to take. Keep in mind this is implicit. So whenever we take derivatives of y, because the independent variable here is actually t, we're going to get dy dt's. So 1/15th y, its derivative 1/15th dy dt. And 1/1500th y squared becomes 1/1500th 2y dy dt. Again, we're substituting in y is equal to 60, and the y prime we had just calculated in the previous part as 8/5. So when we substitute all of those things in, dy dt becomes 8/5, and the y is 60, and the dy dt again 8/5. When you do all the number crunching, use a calculator on this, or just leave it, -8 over 375. Turns out we're going to need this number in a much later part of the problem, but if we needed it, we could use the calculator because it'll be available to us. Okay. Let's move on to part B. Part B asks us to evaluate this integral, but this is an integral that goes from 0 to infinity. So this is an improper integral. We're going to have to deal with that. But we're integrating w prime. Now we know when we integrate w prime, we just get w. So that's actually a helpful thing, and we have a table of w values. We are supposed to show all the work. So if we immediately down here, and I'm going to skip this top line, we recognize that we're not taking the integral of w prime of t, we're taking it of some function of t. So I did a u substitution here. For my 3t minus 25, I let that be u. The du then would be 3 dt. But it's only off by a constant, so I went back and did the quicker method of needing the 3 dt. But if we put in a 3, I put a 1/3 out front. But the integral then, now that I have the 1/3 w prime of u du, would just be w of u. So we're left with 1/3 w of the 3t plus 25, and we're evaluating from 0 to infinity. To deal with the infinity, I went ahead and did this limit. Limit as capital T goes to infinity, and changed out the infinity to a number, t. This allows me to just substitute in the upper limit t, here it is, and the lower limit 0. 0 for t just gets me w of 25. Well, w of 25 comes right off the chart, that's 10. W of 25 is 10. And this is the piece that was a little bit more challenging. We need the limit t approaches infinity of w of 3t plus 25. Well, as t approaches infinity, so does 3t plus 25. So what does w do? This was a big recognition point. Although they did tell us at the beginning, I'm not going to scroll back, that this was a logistics growth function. We know what logistics growth looks like. Here's our little picture of the S-curve. The formula that we were given, I do have to scroll back up. The formula that we were given, if we go back and look at our cheat sheet for logistics growth, remember you can have that sheet out, our carrying capacity sits right here, and it is this 100. So that's the value that things are headed toward. And it is a little bit of a sneaky part of this problem. There we go. But to evaluate this limit, what does W do as t approaches infinity? As its input approaches infinity, it's approaching 100. So that becomes a 100. This evaluates to 30, and that's the answer to part B. Part C asks us to use a left Riemann sum, so from 0 to 45. So here's our little chart again, divided into 3 subintervals, which is natural out to 45. The Riemann sum is simply the delta t times the height, but the height on the left. So the first delta t is 25, and the height on the left is 2. 25 times 2. The second delta t is 5, height on the left is 10. And the third delta t is 15, and the height on the left is 13. Add those up, 295. We need to take 1/45 of the integral, so I did the integral first, now I'm doing the 1/45, dividing by 45, and we end up with this fraction, or whatever decimal version you pull off the calculator is fine. What is it? Well, when you take 1/45 of an integral from 0 to 45, you are finding the average value of the function. So in this case, it's the average number of workers for the first 45 minutes. Part D asks us to do an Euler's method problem here. So I set up the Euler's method. We have our t values, 45, 65, and 85, because it says 2 steps to get out to 85. That makes the delta t 20. In order to figure out the next w value each step along the way, it's going to be the slope given in the original statement of the problem. I wrote w's instead of y's. Delta t is 20, and the previous w value I called w1. Here it is. So this is just a matter of doing the evaluations. Initially, we're going to do, looks like 1/15 w is 30, 1 minus 30 over 100 times 20 plus the previous w value, which was 30. And when we do that evaluation, that gets us 58. So that 58 goes here as the new w value. And then we just redo this process one more time. So this time now it's 1/15 times 58 times 1 minus 58 over 100. And this calculation is just not particularly nice. Times the delta t, which is still 20, plus the previous w value, which was 58. We're just substituting all these things right in. This is going to get us the answer we wanted. This turns out to be somewhere around 90.48 if you go through that evaluation. And that's the w value that we wanted, and that's the answer to part D. So now we look at part E. Is there a time C where w prime of C is equal to 1 between 25 and 45? We've seen this kind of question a number of times when they want to know, will the derivative equal a value in an interval? That's going to most likely be the mean value theorem. So here's my reference to mean value theorem over here. In order to determine this, we have to figure out the slope between 25 and 45. All these values right off the chart, delta w, delta t, and it's 1. I did want to make sure that we can use the mean value theorem. That's assuming that W is differentiable and continuous. They tell us it is differentiable, twice actually to get to a second derivative. But if it's differentiable, that guarantees it is continuous, so I state that. Mean value theorem applies, and therefore we have our answer. Finally, part F here. We're trying to find a second degree Taylor polynomial centered at 65. So I set up my Taylor polynomial method 0, 1, 2. We're looking for second degree, W, W prime, and W double prime. We're doing these at 65, and there's a little bit of carryover from part 1 because we have these two values. We calculated them in part A of this problem. W prime of 65, 8/5. W double prime, if you hadn't evaluated it, we kind of need that now, -8 over 375. Taylor polynomials require the 1 over n factorials, 1 over 0, 1 over 1 factorial, 1 over 2 factorial, and so there we are. And finally, the polynomial piece. In this first one, we really don't need this because it's just 1 to the first power to the second power. So that gets us our polynomial 60 plus 8/5 polynomial minus, I canceled the 8 and the 2, there's my 4, 3/75 t minus 65 squared. To use that to evaluate P2 of 85, when I substitute in the 85s for t, these quantities become 20s. So I just evaluated all of this out, used a calculator, 87.73. That was a lot for this problem. But if you want to go back and take a look, you can go do that. Spend a little more time than I just did. I went through fairly quickly. According to, and I'll be grading this for you, according to my point values, I'm not going to go through all the point values right now, but I'll take a look at what you did, give you some comments, and I will also post a second video on the other one. All right, everybody, that was a lot.